Mabuchi. I'm the director of the Pittsburgh Quantum Institute, and Hideo Mabuchi has kindly agreed to kick off what we're calling a PQI distinguished lecture. So we have lots of people who come in and give lectures, and I think what distinguishes the distinguished lecture, one of the things that distinguishes it is also the fact that we're going to have this interview, this discussion, which will give some more background and depth to what your lecture will be about next week. So really happy that you have agreed to be the guinea pig, as it were, and just to join us in this conversation.
Well, it's a pleasure. Thanks so much for the invitation. It's very kind.
So how are things holding up? You're at home, I take it?
Yeah, sheltering in place at home. I think as an academic, there's a sense in which life is surprisingly little changed by a circumstance like this. Although, of course, everything is upside down. There's complicated things going on in the world right now, and it's kind of hard to plan for the future. That's maybe the most difficult thing about it. But day to day, hanging in there, trying to get through the last couple of weeks of spring quarter teaching.
Right. I guess it's all Zoom University, right?
Yeah. I mean, that's been a change for everybody, especially for all the students. But it's just, especially, I think, teaching a class with students whom you've never met before. It's so hard to kind of get a sense for what's going on, or people following, or it's a.
How many people are in your class? What are you teaching?
This quarter is kind of funny. So I for the past few years, I have been teaching a class which is a kind of a physics and ceramics class. So it normally would combine components where I'd have students in the ceramic studio making work and kind of exploring a certain approach to creative process. While at the same time in classroom discussions, we cover some things like the physics of clay and clay processes, but then also I try to kind of show by example how the kind of creative process that we're working on in the studio really transfers over quite well to scholarly research and even scientific research. But that model, of course, doesn't work when people are scattered all over the world. So it's been a rush to try to salvage the content of the course, even just only relying on things that people are able to do wherever they are.
I see. And your optics or photonics laboratory is also shuttered, right? Still, or?
Yeah, that's a bit more of a cut and dry thing. So up to now, Stanford has been in a state where the only laboratory presence that's allowed are really kind of essential activities that are required to maintain the viability of research, or things that actually happen to be related to COVID-19. But yeah, my students have not been able to really get into the lab for the last couple of months.
Right. Yeah, we're in the same situation, although we're planning to start maybe next week. So maybe by the time you give your lecture, it'll be like day one. Yeah, keeping our fingers crossed. So, so I was, going back in your, your CV. Actually, where did you grow up? Were you, do you grow up in California, or?
No, I was born and raised in Massachusetts. So kind of in the suburbs of Boston. And then went to college in New Jersey, and then came out to California for the first time for graduate school, but have almost continuously been here since.
Right. Well, that's an amazing thing. So, right. So you were an undergrad at Princeton in physics, right?
Mm-hmm.
And then you did your PhD Caltech with Jeff Kimball. And then, correct me if I'm wrong, you went straight into a faculty position at Caltech.
Yeah.
that's pretty badass.
it's convenient if you can swing it.
I mean, well, yeah. I mean, it's. I mean, they basically said, no, you're not leaving, right? And they just grabbed you and said, okay, you're going to be one of the 300, right? So.
Yeah, well, I have to say, Caltech physics at the time really was in a pretty good run of form in terms of placing bets on young people. I think much more so than other top physics departments, there was a belief that it was worthwhile trying to invest in people when they were really young to try to help them kind of grow into something special, both as a way of trying to help young scientists do more than they otherwise might be able to accomplish at another place over the same span of time, but also as a way to seed the growth of the faculty and the activities in the department. So I was incredibly fortunate to have been in the right place at the right time, kind of doing the right thing to be a part of that sort of initiative. But yeah, no, it was great.
Did you feel like it, so I guess in a time when you were a PhD student, did you feel like you were like there was a transition internally, even though you were a PhD student and you were doing things more independently, or you were like a postdoc but without a PhD, or like was there? I mean, how did that transition take place? Because this is often students when they graduate, they're wondering what do I do now and so forth, and just kind of curious like how that transition actually took place.
Yeah, I mean, I think there definitely is a major transition there. I would say that, maybe in a way that started already as an undergraduate. As some in your audience may know, at Princeton, there's a mandatory undergraduate thesis. And so that's taken really quite seriously at Princeton to the extent that you have a reduced course load your senior year. So many students will actually get started on their senior research thesis the summer before senior year, and then it's the main thing that they're doing kind of in a way for their final year in college. And I think depending on the situation of the group that you're in, you can find a lot of freedom to kind of make your own way into a research project there. So I think, that was definitely the start. And then, again, I was very fortunate in Jeff Kimball's group. He gave me really a lot of latitude to explore new ideas and things, even in the early years of being a graduate student. So, by the time that I was a senior graduate student, I and other members in Jeff's group were sort of used to the idea of proposing new topics and sort of just forging ahead and getting things started that then might or might not be picked up by the group. But perhaps I think in the spirit of what you were asking, I think right around that time I had an interesting conversation with a friend of mine who was a little bit further ahead in the kind of career path, and he made a really important comment, which was actually making that transition from being a student to being a faculty member. The most difficult thing in a way, and the most important thing, is learning to take yourself seriously. And that was good advice at that time that I think really was important in the big picture.
So I think it's also clear that a lot of people around you were taking you seriously, and I just want to now cut to this this photograph. And if you can see it yet, it hasn't shown up on my screen. This is from 1994. This was a meeting, like one of the first quantum computing meetings, and maybe you were one of the very few graduate students at that meeting. I don't know, is it showing up? Yeah. So do you recognize yourself?
Yeah, just barely. I'm the one near the front with my eyes closed.
And I guess you were caught blinking, but there you have like Charlie Bennett, Peter Shor, David DiVincenzo, Sirac Zoller, and so forth. What are your memories of that meeting?
That it's a little bit hard for me to disentangle that particular meeting from, that was part of a series. So I think that must have been the first one that I actually went to there. But at Villa Guilino in Italy, they had a series of these meetings that were at least once a year, and sometimes they happened more than once in a 12-month span. And it was it was a highly overlapping crowd that went to those from year to year. So that entire sequence of meetings, I think, is all kind of blurred together. But this particular crowd that you're showing on the screen right now, that's definitely a community that I strongly associate with that time. Some people are still working centrally in quantum computing, others aren't. But I definitely think back fondly at that time. And the thing that I remember most of all was the sort of very open eagerness that everybody had, I would say, to share ideas and to try to find common ground in terms of what we were interested in thinking about. And most of the time, what would happen in the evenings and over coffee and such was people explaining what they were doing and what they were interested in. And it was an early enough moment in the development of quantum information science that you could kind of keep up with all aspects of it, at least at some overview kind of level. So that was a really
Yeah.
neat.
Yeah. I mean, these pictures were stolen from a perspective article that David DiVincenzo wrote about the DiVincenzo criterion in quantum computing at the time. Like you said, there was a time once when you could actually keep up with what everything that was happening, but probably not so much today. Things have really kind of spread out quite a bit, and I was looking at your website, and you have spread out into a large number of areas. This is supposed to be, I guess, a category cloud of different research interests in quantum materials and biophysics, and I guess we'll be hearing about coherent Ising machines, and I want to talk about that a little bit more today. I would say maybe, is it correct to say that that sort of quantum control is in some sense a very large overlapping theme in your research? I mean, are you a control freak?
So control theory, I think you're obviously an exception, but I think in physics in general, I think control theory is a field that's not really, it's not so recognized maybe amongst most people who work in the field of physics. But I look back at it as when I was a graduate student working in the lab. Together with Quentin Turchette, we were working together on an experiment, and we had to do some feedback stabilization of cavity lengths or something like that. And I remember being extremely impressed that if you read like an introductory first-year graduate textbook on feedback control theory, it was theoretical, but kind of that theory that you learned was immediately relevant to stuff that you were doing in the lab, which really hit me as kind of, other than like learning a computer programming language, there's very little theory that's like that anymore in physics, where it's just the beginnings of it are just immediately applicable and help you to do things that you're really interested in doing. So, that led to just the realization that, the things that we were trying to do in cavity quantum electrodynamics at the time, they were very much along those lines of trying to do feedback control, but now at the level of quantum systems in real-time evolution. That then turned into a research interest in generalizing that theme and kind of looking into how you could take some of the sophisticated design tools that one has in engineering control theory and applying them to quantum systems. Of course, in the process of getting interested in a topic like that, you realize that other people have already done a lot in that area too. But I think moving off into that area, which was not very mainstream at all in AMO physics at the time, that was really very formative. And I think I've retained that sort of interest in what you might call connecting fundamental things in engineering to things that we're doing in quantum systems. And at the moment, I would say that we don't really do that much that is so focused on control theory. But I think the spirit of what we're doing retains the kind of spirit that comes from that field. At Caltech, while I was on the faculty, initially my appointment was just in physics, but at some point halfway through my time there, I picked up a joint appointment in control and dynamical systems, did a little bit of teaching over there, interacted with the faculty quite a bit. And so I'd say some combination of the perspective on dynamical systems theory and just what it meant to think deeply about engineering, design, robustness, that kind of thing. Those things have definitely been very formative in shaping what I'm interested in. And so, things that we're doing now, I would definitely characterize as quantum engineering, and engineering in the spirit of what I learned from my colleagues in control and dynamical systems, even if the specific topics that we're working on at the moment maybe are a little bit less focused on control theory per se.
Right. So so maybe it's a part of your tool set. It's a part of how you think and approach things, but it's not the focus of what you're doing at the moment, I guess.
Yeah.
Is that maybe what you're saying?
Yeah, it controls the perspective, right? But we're not really publishing in controls journals, or we're not usually giving presentations at controls conferences anymore.
So there's another quote that I found really interesting on the website, which is, the greatest challenge may be to find the discipline not to let the revamping of core engineering methodologies too narrowly driven by the earliest insights of 1990s quantum computation. So it's interesting because you were there, like you were there at that, at the outset. And I think maybe what you're saying is that there's sort of an orthodox way of thinking about how to build a quantum computer, how to satisfy Division criteria, how to scale up number of qubits and universal gate sets and Shor's algorithm and so forth. And maybe that's too narrow of a way to think about how quantum systems can be utilized and expanded upon. So, I mean, is that a correct interpretation of what you're saying?
Yeah, generally speaking, that is the general idea. I mean, I sometimes when I give talks, I go into this as a bit of a screed. The way that I look at it these days is, as people started to think about quantum computing, and especially with Shor's algorithm, which really kind of kicked things off into overdrive, there was such a temptation to say that, well, conventional state-of-the-art computing is based on bits of information, deterministic binary computation, algorithms as we know them. And so you could just slip over in a very easy way to say, oh, if you have bits, then we could think about quantum bits. And so if we have quantum bits, we can think about quantum logic gates. And from there off you go in kind of building the digital hierarchy in terms of how we think about algorithms and error correction and such. But that was certainly the most fruitful way to get started. But then, if you think about what's happened in the 25 years since then, I sometimes like to make the provocative claim that we haven't really made any fundamental progress in this field since the late 90s, maybe since the realization that it is possible to do quantum error correction. And anytime we start talking about, doing things like factoring at large scale, the overhead that's required for quantum error correction and fault tolerance is just so extreme that you wonder if we've missed something. Because it would be really strange in a way if you would claim that, if we make kind of a one-dimensional spectrum with conventional computing on the left-hand side, and then perfect fault-tolerant Peter-Shor type quantum computing on the other side, and the coordinate in the middle is something like, you could call it something like the rate at which you can do logic gates divided by the rate of decoherence. I mean, if it's really true that you have to get almost all the way to perfect performance, and then there's this sharp threshold at the fault tolerance threshold, that suddenly you get exponential gains in performance, but there's nothing to be gained in between, that would be really weird, I think. And I have to wonder if the problem is something like, well, yeah, if you insist on it, you can think about information processing in realistic, partially coherent quantum systems in terms of things like quantum bits and quantum gates and quantum algorithms. But it's actually not a natural mapping. And for that reason, it's very inefficient to try to realize that abstraction in actual hardware. That if you go back to, well, where did bits and deterministic binary computing come from in the classical world? It has to do with, oh, well, we can make a bit as a sensible thing because we have transistors. And we can, and we have transistors. There's this kind of thing as the amplifier abstraction in classical electrical engineering, and all kinds of things like that. But we know that you can't make a reasonable amplifier abstraction in the quantum world. And so why are we starting all the way up at digital computing models? Shouldn't we kind of be looking down below to see if there isn't some other way that we should be thinking about information for partially coherent quantum systems? And so I worry that somewhere along the line, we really have to go back and do a lot of re-engineering to totally rebuild the abstractions that we use to think about computing, so that they're much more naturally matched to what we can actually do in realistic quantum systems. And that's kind of the perspective in this book.
But are we really throwing out the idea of a quantum bit or like a quantum two-level system? Because things can get really complicated if you start talking about qubits and things like that. I mean, or just really like vague notions of quantum coherence of an indeterminate number of quantum subsystems. I mean, how much do you need to, like, what are the parts that you really want to keep versus so I mean, I guess when I'm thinking about your this quantum Ising, a coherent Ising machine, I'm still imagining that you have bits. Okay, maybe they're coherent. Maybe you don't have all of the the types of gates that you would like to have in a quantum computer, but there's still a number of two-level systems that you are working with. Isn't that right?
It is and isn't the case. I mean, I think the abstraction that's maybe problematic currently in quantum computing is the idea of an ideal qubit, right? So you can think about an ideal qubit, one without decoherence and one that can be freely entangled with anything else you want to. You can make up that abstraction and work with it, but it's really not very, it doesn't map very well onto real systems. So maybe that's not a good abstraction to use in the way that you think about designing information processing systems. Where something like the coherent Ising machine is concerned, I would actually say that the fundamental abstraction, at least at the current moment, is something very different. It's really much more in line with what somebody like John Hopfield was thinking about in terms of artificial neural networks, where kind of what we're doing is taking some number of systems. You can think of them as bits, although fundamentally we're working with optical parametric oscillators, right? So they're fundamentally nonlinear oscillators. And you try to couple them together and create a schedule for some of the gain parameters in such a way that, if you have some gain that you're going to ramp from 0 to a high value, by the time you're at high value of a gain parameter, you know from basic principles that the overall phase portrait for this thing viewed as a dynamical system is going to have a single kind of strongest mode of oscillation that corresponds to an optimum solution to an Ising problem. But then fundamentally what you're trying to do in this design is to say, I would like to figure out how to design the couplings in this Ising machine and the way that I ramp certain parameters such that I know where to start in initializing my machine, such that as I flow through this analog phase portrait, eventually I have a high likelihood of ending up in the basin of attraction of the global optimum or of some very good local minimum. And so I would say the abstraction there is not a bit abstraction at all, right? Fundamentally the whole system really lives much more in the world of dynamical systems theory, topology of phase portraits, basins of attraction, that kind of thing.
So it's the journey, it's not the destination, maybe, because the destination, of course, is the solution to your optimized problem, but exactly how you go. I mean, the way you're describing it sounds a lot like the sort of adiabatic, I don't call it adiabatic quantum computing, where you have some parameters that you're tuning, and then eventually you're at the end point when you turn up the strength, maybe to the maximum value, then you're in a very well-defined ground state, but it's some design considerations and so forth. Is that? I mean, so there are other. So I guess one question I have is, how does this differ from other types of adiabatic, quantum computing or adiabatic optimization approaches?
So there's certainly a similarity there, as you point out, but I would say that from what we understand about coherent Ising machines, their evolution doesn't need to be adiabatic in any sense, right? It's, since we're basically talking about a bunch of coupled oscillators, right? So we're working in a continuous variable sort of phase space. And so, if we first think about kind of a mean field picture of the system, so we think about the classical limit of a CIM, then, you are at every point in time at some point in the phase space. And as you vary parameters, the kind of topology of the phase space in terms of where the separatrices are, what's an attractor, those kinds of things, that is changing around the current state of the system. But there's no sense in which you're going to adiabatically evolve, always sticking close to some fixed point. So it differs from the idea of adiabatic computing in that way. And so, but we're much more in the business of trying to say, how do we kind of create this kind of bubble of phase space around where we think we are, such that we're going to know where to get started and figure out how to guide that bubble of phase space into something that will eventually be in the basin of attraction of some solution that we like. And so it's related to adiabatic quantum computing and things like that, but I think it has a lot more design degrees of freedom, which may be good or may be bad. We'll see.
So is there a notion of dissipation or analog of dissipation also that happens in your system? I mean,
Yeah, definitely. Whereas it's most natural to think about adiabatic quantum computing in a perfectly Hamiltonian setting, and just to imagine that you're going to follow along this ground state. Sort of from the outset, coherent Ising machines are formulated in a world of driven dissipative systems, right? So there's always very strong dissipation acting, and the systems are strongly driven. So you kind of have to model them in an open quantum systems kind of approach. Yeah, rather than talking about ground states and spacings between levels, it's really much more natural to take this engineering dynamical systems kind of thing where you'll have things like attractors, right? You don't have attractors without dissipation. And so in principle, this can build in a degree of robustness that's maybe not possible in a purely Hamiltonian setting. On the other hand, it's a little bit more difficult to kind of visualize how it is that you might ultimately want to take advantage of quantum coherences and things like that.
so in terms of scaling, so I was looking at, you know, one of your one of the papers from a few years ago. This may be all outdated now, but it was talking about 100-spin coherent Ising machine with all-to-all connections. So this is, I guess, one particular example where you have 100 spins and you have this incredible degree of control. And I guess this is in some sense a dynamical system, although this Hamiltonian doesn't have a dissipation term in it. But I assume that that's something that also is ends up being added to the mix when you're trying to figure out. My question was though is like how scalable are these? And like you were saying with Shor's algorithm, you can factor 15, but can't do anything useful. What is the threshold for it being more powerful than the fastest supercomputer at solving problems? And what is the goal? Like how many spins do you need, and what are the limitations right now?
So that's the big question in a field like this, of course. And I think anybody that you ask who's working in the field will give you a slightly different answer. So I'll try to sneak up on my answer, and if we have time, maybe since you've got a Hamiltonian on the screen, I can go back and address that connection between Hamiltonians and dissipation again afterwards. But so in the world of coherent Ising machines, we're in a very unusual sort of situation in that we're doing something that feels like computer science, but it's actually experimentally driven. So in terms of scaling and how many spins will it be possible to incorporate in a coherent Ising machine while retaining this ability to program arbitrary all-to-all connections, which is really kind of essential for the application's interest. It's really being driven by kind of prototyping work being done mainly at NTT Basic Research Labs in Japan. So they have a sizable investment in building larger and larger machines. So there are operating machines now in the thousands of spins kind of range, and there are plans underway to go substantially larger than that. So the question is, how does that compare to what you're able to do with conventional technology? And there, the answer becomes a little bit complicated. So maybe with reference to this Hamiltonian that you've written up there on the screen, and let me for the moment ignore those the local terms there in the second summation. But if we just look at a term that's like sum on I and j of some coefficient matrix jij times the value of spin I times the value of spin j, that's of course the famous Ising Hamiltonian that we know from many-body physics. And one thing that you can say in a rigorous fashion is that if you talk about asymptotically large problems of this size with really arbitrary sort of jij matrices, finding a guaranteed global lowest energy solution, lowest energy solution for this Hamiltonian, where the sigma i's and sigma j's are binary variables, finding that guaranteed global optimum solution is an NP-hard problem. Now, I don't think anybody really believes that something like the coherent Ising machine is going to be able to solve that particular problem with anything less than exponential scaling. So I don't think that that's really on the table in terms of a driver for why people are doing this. Really, with coherent Ising machines, we're effectively in the business of heuristics. So what we're trying to do is find really good solutions, right? So really low energy solutions for this problem in a really short time. And in fact, I think in practical applications where people are interested in solving Ising type problems for logistics or drug design or things like that, those sorts of applications. They're also interested really in getting really good solutions in a really short time. And so the kind of question that's going to come up is, how are coherent Ising machines different than conventional computing approaches? It's based on a completely different technology. The kind of strategy for finding solutions is completely different. So I think what may be quite plausible is that as we go to seriously large problem sets, we'll find some cases where there will be instances of the JIJ problem definition matrix for which CIMs are faster in some absolute sense than competing conventional approaches at similar expense and energy consumption. And so, as far as we can visualize where we're trying to go in terms of practical impact, I think that's the roadmap in the near term. At the same time, like I don't think that I'm in this field for practical impact. What I really like about the coherent Ising machine is it gives you a concrete architecture in which to ask questions about in what ways does it make sense to create hybrid information processing systems that use both optical signal formats and electronic logic, as the current versions do. And furthermore, it's a really interesting context in which to start thinking about sort of perturbatively introducing some quantum dynamics to see what sort of effect that has on the speed of solution. So I think, we really have a lot to learn by pushing forward in this investigation of coherent Ising machines, but it's it's very different than mainstream quantum computing in the sense that in the coherent Ising machine business, we have some relatively large-scale prototypes already in operation that empirically are performing at an interesting level, but we have no theoretical analysis of what the scaling is meant to be. So we don't have that draw for the long run. So, compare that to Shor's algorithm, where for a long time now, right, over 25 years, we've had this interesting theoretical result about asymptotic scaling, but it takes really a lot of effort to get going in terms of building even small prototypes.
Yeah, no, it's really exciting. So I wanted to shift just gears just a little bit. So you have this whole other side view, and you hinted at this in the beginning. Basically, this interest of trying to, integrate, sort of what I call like arts, ceramic arts, and craft with modern science. And I guess in your course that you're teaching, you're doing this to some extent. And then you also use the phrases aesthetic philosophy and new materialism, which I didn't really understand. So if you could explain what that means and what the connections are, I'd really be fascinated to hear.
Yeah, so there are some points of connection and other things which are just complementary. Maybe I'll start with the easier part of just kind of talking about ceramics in the context of what I do as an academic. So, I mean, I just have an independent interest in ceramics and other forms of traditional craft. I put a lot of time, of my own time, into making things, and I've just found that a really valuable complement to kind of being a scholar. That as a physicist, even as an experimental physicist, by the time you're a faculty member, you spend a lot of your time just kind of thinking about stuff. And so it's great to have a context like a ceramic studio where you can go and just kind of do things with your hand and things are what they are. But also, I would say that my interest in ceramics has got me reading very broadly about a lot of things and then thinking about connections that do or don't exist between traditional craft ways of understanding materials and thermodynamic processes like firing, and how a physicist looks at those. Like, I as a physicist, having learned my physics first, I can't go to a traditional wood burning kiln that's firing ceramics. I can't go there and not think about the physicsy questions of what's happening, like surface color development on ceramics where there are no applied glazes, but you're just looking at the kind of natural interaction between trace metals that are in clay, which is just weathered minerals of the Earth's crust. You stick those things in a wood burning kiln, so they're interacting with whatever gases come off of burning wood at high temperature. There's a lot of oxidation reduction kind of stuff that happens. I can't look at those things and not wonder what's going on at a physics level. And so that's led me into some personal research where this was a great excuse for me to get trained up in using the SEMs and micro-Raman instruments, other things like that we have available at a place like Stanford. And so I have my own little personal research project of trying to understand in a physicist's terms what's happening when you fire ceramics and how colors develop. And so that's just been, it's been nice for me, right? Because I can have my own research project like that that doesn't really require much funding, that I don't have to give up to my students, and where I can make progress on a few hours a week.
That's
That's
so
been,
cool.
right, this has been really neat. But it has also turned into things. And like well, just a couple of terms ago, we taught this really interesting course where I partnered with people who are art conservators at the De Young Museum and the Legion of Honor in San Francisco. And we did a class that was sort of about conservation science. We called it Physical Analysis of Artworks. And so I had, we had 8 students in the class, none of whom had really a STEM background, at least not a physical sciences background. But we brought them in and we kind of talked about the process of conserving artworks like paintings. And we got all of them trained up on the SEM. And so they all did course projects that involved looking at actual samples from artworks that were undergoing conservation work at the De Young and the Legion of Honor. They looked at those samples using the surface analysis equipment that we have and returned some information of value to the conservators at the museum. So, you know, one of the things that we stress out about quite a lot at a place like Stanford is trying to revive the idea of liberal education and in kind of preventing the university from becoming effectively a pre-professional school for people who want to go write code for a living. And so I think, you know, coming up with these sorts of courses where you really, you know, take things like ceramics or other forms of artwork and look at them both from a sort of humanistic artistic lens and from a scientific lens, I think it helps to restore this idea that the different subjects that you can learn about in university, they're all part of a continuum, right? We shouldn't be thinking in terms of a strict divide between, what do they call them, techies and fuzzies or something like that. But that, you know, really you get the most value out of an educational experience by sort of immersing yourself in all of these different aspects. And so, that, you know, going forward, that's an important thing for me in terms of thinking about how I put my time into my teaching.
So I remember when you visited Pittsburgh, it was a number of years ago, you said that you were learning Sanskrit at the time. How is the Sanskrit coming along?
That fell by the wayside. That must have been a really long time ago. I think that fell by the wayside and turned into, I spent a few years learning Spanish. My wife's a native Spanish speaker, and so this became a priority. And then in more recent years, I've been putting more effort in trying to learn how to at least read some Japanese. So you know, I would say that that interest in foreign languages definitely kept up, but circumstances has led me into other parts of the globe.
It just seems to me that you have a very diverse, you know, intellectual and creative interests, and you know, as a faculty, and you know, in your position, you have this ability to do essentially what you like, right? You follow your interests, and as they wax and wane, and then yeah, I guess it's a nice job, right?
No, it's great. And, you know, it comes back to something I was saying earlier that I think the largest barrier that you face, if you're a tenured faculty member, you know, you do have a lot of control over how you direct your time. You know, your colleagues may make snarky comments, or, you know, you may feel like you're not living up to expectations and things. But really, you know, a lot of it is about getting over your own self-inhibitions to not evolve and change and acquire new interests and pursue them seriously. But yeah, at a university, there are so many opportunities. You know, just to answer this other thing that you brought up about aesthetic philosophy and new materialism, you know, there I had become interested in things about, you know, one of the things that really lack in ceramics and traditional craft is there's a paucity of good critical writing, I would say, about traditional craft. That had me reading certain trains of thought in aesthetic philosophy. But then last year, I had an opportunity to co-teach an anthropology class with somebody who was very interested in kind of looking at what's called the new materialism in the social sciences. So it's a certain body of social science theory that relates to what's going on in aesthetic philosophy, but it's really about kind of material and things. So we tried to conceive of a course that would really be kind of multidisciplinary in the sense of thinking about things and dynamics and evolution, both in the way that a social scientist looks at them, but also in the way that a physical scientist looks at them. And so, yeah, you know, those kinds of growth experiences have been there, and I would say have been very influential in terms of how I choose to spend my time on a day-to-day basis now.
I look forward to reconnecting with you next week.
Thanks. No, it's been a lot of fun. Thanks for the opportunity to do this. And yeah, I'll see you next week.